Epinephrine, which is also adrenaline, those are the same thing, is literally manufactured from the molecule dopamine. If you look at the biochemical cascade, it is dopamine is converted into adrenaline, which is the basis of all energy, all neural energy. And so, including thinking. And so if one is not in a place of being able to set their goal on a particular lofty goal, a graduate degree, a book, etc., yet, the way one gets to that is by completing things in their immediate environment from start to finish and closing the dopaminergic loop.
Those are at least micro-narratives, right? So they're not integrated across a long span of time, but they're not nothing. And so one of the things, well, I did write about this in my first book, particularly about putting your house in perfect order. It's like, well, if you're lost, one of the things you can do is look around and see what direction you could take locally, is fix something. Hello, everyone. I'm pleased today to have with me Dr. 앤드류 D. Huberman. He's a neuroscientist and tenured associate professor in the Department of Neurobiology at the Stanford University School of Medicine. Dr. Huberman and his lab have made contributions to the brain development, brain plasticity, and neural regeneration and repair fields. His work and his lab's work focuses on the visual system, elucidating the nature of neural mechanisms controlling light-mediated activation of the circadian and autonomic arousal centers in the brain and mediating conscious vision or sight. His lab investigates how the brain works, how it changes through experience, it's a field known as plasticity, and how it repairs itself. He and his colleagues have worked to discover strategies for halting and reversing vision loss in blinding diseases and understanding how visual perceptions and autonomic arousal states are integrated to impact behavioral responses. His lab employs a large range of state-of-the-art investigative tools, virtual reality, gene therapy, anatomy, electrophysiology, and imaging and behavioral analysis. In January 2021, Dr. Huberman launched the Huberman Lab Podcast, concentrating on neuroscience and other scientific topics. It's done phenomenally well for a detailed scientific podcast, attracting 1.5 million subscribers. It's very good to see you today, Dr. Huberman, and thank you for agreeing to talk with me.
Oh, delighted to be here. Your first book, 12 Rules for Life, sits prominently on our bookshelf in our living room, and we've all read it and learned a tremendous amount from you over the years, and certainly feel a kinship because of the shared relationship between university professorship and public education as well.
Right. Yeah, well, we've got lots in common. I'm particularly interested in the neurological work that you've done on both anxiety and exploration, although there's plenty of topics to talk about today and plenty of overlapping interests. But it's been a while since I've reviewed the neuroscience literature pertaining to both anxiety and exploration. And so maybe we could start by you laying out what you've discovered and how you're thinking about what you think anxiety signifies, how it's related to exploratory behavior, which I think you described as something approximating courageous approach, although you were talking about mice in that particular paper, and what you're thinking about with regards to the neural basis of these different behavioral responses, behavioral and emotional responses.
Sure, I'd be happy to. And I should mention that these days my laboratory mainly focuses on humans. We still do some mouse work, but we in partnership with people in psychiatry, we're doing essentially equivalent experiments in humans. So I'd be happy to elaborate there. You know, many people perhaps, but not everyone, have heard of the autonomic nervous system, which simply means automatic. It's a bit of a misnomer because without going too much into the history of that, if you look back to the origins of medicine in the time of Galen and so forth, when they were first, dissecting cadavers and whatnot, there was this idea of a nervous system, or a portion of the nervous system eventually came to be that could control so-called vegetative functions, meaning the rate of digestion and the really what neuroscientists typically think of as boring stuff. But it's anything but boring. It's the stuff that keeps you from urinating while you're asleep, unless you're a very young child, right? And it's the stuff that keeps your digestion going as you command your attention to other things. The autonomic nervous...
Right. It's all the things It's all the things that are too complex for us to think through.
That's right. And they are, as you point out, immensely complex. And, nowadays with all this interest in the gut microbiome and things of that sort, I mean, these are tremendously complicated operations that are happening generally below our conscious awareness and that are indeed vegetative. They can be controlled by emotion. We were all familiar with the idea that when we are emotionally distraught, that our digestion can be different or et cetera. But typically, we can't control, for instance, in a conscious way, the rate of our digestion or the speed of our heartbeat in any kind of direct way. We can have a particular pattern of thought to control those. But in general, those functions were thought to be vegetative and outside of our conscious control. And the name autonomic nervous system sort of swallowed and overtook the vegetative part. So it includes that, but also three main aspects of body to brain signaling. And those three aspects are heart rate, could be quickening or slowing of heart rate. We are and we can be very aware of that, some of us more than others. Gut and especially the chemical composition and the extent to which our gut is empty or full. So heart, stomach, and then rate of breathing and sort of depth of breathing, meaning how much air we have available to us. And I think the three main ways to think about the way that the brain and body communicate is that it's either going to be mechanical or chemical. Let's use the gut as an example. Your stomach can feel acidic, or it can feel nice and warm and fuzzy, whatever that is in a chemical sense. Your heart rate can feel like it's going at a rate that's appropriate for your circumstances. If you're running, it could be quick. And if you're sitting in a chair quietly at the doctor's office waiting to be called back there and all of a sudden your heart starts racing, then you would think, well, that's appropriate for that situation, but it's uncomfortable, right? It's out of sync with what you are doing, which is sitting. So there's mechanical information and then there's chemical information. And with respect to your lungs, you can feel like you're out of air or you have plenty of air. You can feel like your breathing is labored or it's easy, or in the chemical sense that the air that you're breathing, your lungs are burning or it feels easy to breathe. So basically there's chemical and mechanical signaling from the body to the brain, and the brain interprets all of that. And we put all of that under the umbrella of the so-called autonomic nervous system. And the autonomic nervous system can really be best thought of along a continuum. And here I'll avoid complicated nomenclature, but I'll throw it out there for the aficionados. Some people have probably heard of the parasympathetic and the sympathetic. That naming is a little bit misleading. Again, what we can really think about the autonomic nervous system as is a continuum, or more like a seesaw, of at one end is alertness, and at the other end is calmness. Right? That is translated to the so-called sympathetic and parasympathetic nervous system, but I'll call it the alertness and calmness system just for sake of simplicity. So it's sort of like a seesaw, and it has different neural circuits, and basically whether or not you feel very alert or panicked or alert but calm or a little bit of anxiety, that's going to depend on the balance between this alertness system and the calmness system. If you're having a full-blown panic attack, then the alertness system is, it's as if the seesaw is tilted all that way. If you're deeply asleep, well, then the calmness system is really tilted down. You could say that's a portion of the seesaw. This is all kind of obvious and dates back, 100 years or so, which isn't that long in the history of science, but we've known this sort of thing for a while. Okay, what's interesting and I think more relevant nowadays is to think about one's own interpretation of those signals and how that relates to anxiety and, as you pointed out, exploration, and then to think about where the nodes of control are. In this seesaw model that I'm putting forward, the seesaw has to include what I would call a hinge, a location in the middle in which you can voluntarily adjust the seesaw to either be more tilted toward alert or more tilted toward asleep. And for many people, they find that their overall level of autonomic arousal is either inappropriate or inadequate for the demands of their life. Inappropriate meaning their heart is racing, they feel more jittery, more as if movement would be the default and worry would be the default and anticipation is the default than is appropriate for their circumstances. Waking up in the morning and feeling stressed, for instance, immediately without any immediate cause or maybe stress about real life events. For other people, they feel more exhausted than they would like. They're having a hard time leaning into the pressures of daily life. Both of those, even though they have sort of polarized phenotypes, they look very different. In one case, over energized, and in one case, under energized. Both originate within the autonomic nervous system. And we can reliably say from work done in animals and humans that that is not the consequence of the alertness system or the calmness system being disrupted, but rather that hinge in the middle is dysregulated. And we now know what that hinge is. And this is based on work done by colleagues of mine at Stanford, in particular a guy named David Spiegel, who's our associate chair of psychiatry. He's done a lot of work, and his father did a lot of work in the application of clinical hypnosis, not stage hypnosis, but clinical hypnosis for the treatment of various things. But his work and some work in our laboratory now has shown that there's an area of the brain that you are familiar with, Dr. Peterson, which is the prefrontal cortex, and in particular, the left dorsolateral prefrontal cortex, if you really want to get down in the weeds about it, that has direct communication with two brain areas that are absolutely critical for this issue of whether or not you feel right for your circumstances, whether or not you translate that into a curiosity and exploration, or whether or not you translate it into this thing that we call anxiety. And those two areas are called the anterior cingulate cortex. Again, I apologize for all the names, but the anterior cingulate cortex and the insula. And I think if I were to make a prediction about what the buzzword is going to be in popular neuroscience in the next 5 years, it's not the amygdala, it's not the prefrontal cortex, it's the insula. The insula has a couple of different regions, but one of its primary regions, the front end, the anterior insula, is responsible for interpreting all those bodily signals. It essentially is a funnel for all those signals about breath rate, heart rate, conditions of the gut, whether or not your body feels ready to move or exhausted, et cetera. And that all funnels into the insula. And then also coming into the insula is information from classical areas like the amygdala, which are involved in threat detection and fear, and also emotion and memory. So the insula is really this incredible hub of information about somatic signals, about bodily signals. And then the prefrontal cortex, the dorsolateral prefrontal cortex in particular, is in communication with the insula and literally makes a...
So let me ask you about that. So does that mean that, the body in some sense is reporting to conscious awareness? Now, it reports unconsciously in all sorts of ways too. So it might report to the hypothalamus, which is a very low-level brain control area, by the way, for those of you who are listening. It might report to the hypothalamus primarily unconsciously. But do you think it's the insula that's reporting on the nature of bodily states to the prefrontal cortex in a manner that allows us to be consciously aware of our body states?
That's exactly.
Is that part of that integration system?
That's exactly right. You're exactly right. The insula sits as a different sort of station in that it's reporting to the conscious areas of the brain, to the prefrontal cortex.
Right. So we can take our own physiological state into account then when we're envisioning plans, because part of what the dorsolateral prefrontal cortex does is allow us to envision different possible futures. And those are plans. And you're not going to make a plan to run 2 or 3 blocks to get to the corner store if you're so exhausted you can't get out of bed. And you need a reporting mechanism that tells you what physical state you're in so that you can predicate your plans on that. You think the insula, at least in part, is responsible for formulating those representations or for reporting those representations.
That is exactly right. In fact, the animal data and the human data, both lesion data and reversible inactivation data, support that in humans. So you have that exactly right. And as you mentioned, the prefrontal cortex, it gets sort of thrown out there for everything. I think, nowadays people have probably heard of the prefrontal cortex and people hear about executive function, which of course is true. But if we were to really dial back and say, what is the prefrontal cortex in the position to do? It's a flexible rule-setting structure. How do we know that? I'm sure you are probably more familiar than I am with the classic Stroop task. You give somebody a bunch of cards with different words on them, and those words are written in different colors, and you tell the person, okay, just read the words to me. Ignore the color that they're written in, just read them. And so they're saying they're cat, dog, shelf, book, professor, student, etc. Then you quickly change the rules and you say, you know what, just tell me the color that the words are written in, but ignore what the words say. And people will do that, but there's a portion of time in which they slow down a bit. It's actually hard because you've done a rule switch. Much of life, as you know, and again, this is more your domain than mine, is about applying different rules in different contexts. Now, what we know is that the insula and the prefrontal cortex are both intimately involved in this conversation that establishes which rules are appropriate for a given situation. So for instance, if somebody were to say something that quote unquote triggers me. Okay, I'll use myself as the example, right? Maybe someone will tweet something and I'll think, and I immediately want to respond in a way that I know I can kind of flip them on their back immediately. But then I think, maybe I want to refrain from that for any number of different rules or reasons, right? Well, then I'm starting to apply different rules. I'm starting to think about the context that's outside of the autonomic response. Because in a strict, very animalistic way, in other words, in the absence of an insula and a prefrontal cortex conversation, really the only thing an animal or human needs to do is just respond to their arousal in, it's either, you can either retreat, you can stay put, or you can fight, right? That's really the only three major.
And those are very fast responses generally. So let me ask you about the role of the prefrontal cortex in what you described as rule switching, because I would like to know what you think about whether or not the prefrontal cortex is actually, let's say, switching rules, or if what it's doing is switching context-sensitive behavioral patterns that when we talk about, we describe as rules.
Big government continues to spend borrowed money, inflation continues to swell, dragging down our economy, and the stock market has entered bear territory. So what's your plan? Are your assets diversified? I'm Philip Patrick, precious metals specialist for the Birch Gold Group. For nearly 20 years, we've helped Americans diversify into gold, and we can help you too. Did you know you can own physical gold and silver in a tax-sheltered account? We can help you transfer an IRA or 401k tied to stocks into an IRA in gold. If you're skeptical about the trajectory of the economy in the US dollar, then text Jordan to 989898. Birch Gold Group will send you a free info kit on securing your savings with gold. With thousands of satisfied customers, 5-star reviews, and an A+ rating with the Better Business Bureau, we take precious metals seriously. Text Jordan to 989898 for your free info kit.
It is the critical question that you're asking. The prefrontal cortex, in particular the left dorsolateral prefrontal cortex, is in an incredibly unique position to not only establish different rules depending on context, and the way it does that is by accessing memory. So the hippocampus has access to prefrontal cortex and vice versa. It's almost always a reciprocal conversation. So it can pull memory thinking, the last time I responded like that didn't get me the result I wanted, or the last time I responded in this other way, I got the result I wanted. Again, regardless of situation. The other thing that the left dorsolateral prefrontal cortex is exquisitely positioned to do, and this is beautiful work of a colleague of mine by the name of Nolan Williams, also in psychiatry, is because of its connections to some structures that then feed into the vagus nerve, it actually can slow the heart rate down. So in other words, let's say someone says something and your immediate impulse is to fight or to respond in a kind of knee-jerk way. If you halt, right, I guess what the meditators and the mindfulness folks was called the gap, or if you can access some memory and think, and you might be thinking, actually there's a much better way to place the dart if I just kind of lean back a little bit, or it could be, silence might be the best response, right? Or it could be that you're going to carefully access some data from your hippocampus to respond in a way that is most effective. For instance, here I'm talking about confrontation, but it could be any situation. The left dorsolateral prefrontal cortex does two things. As it acquires a new rule set or starts to access information about a new or possible rule set, it also sends a parallel signal to slow the heart down through the vagus nerve. And that is, I think, one of the more important and fascinating discoveries in the last 5 years. Those aren't data from my laboratory. I wish they were. But it's very clear that when we start accessing alternate rule sets, there's a signal that quiets the body in some ways and positioned.
Is that partly how you calm yourself down?
That's right. It is how you calm yourself down. And again, you have the clinical background, not I. But I'll confess I've been in therapy enough to know that occasionally, one feels as if you're accessing some piece of info as the patient side. I can only report from the patient side. Accessing some what feels like important piece of information. You're pulling on a thread of some sort, but then the therapist will say something, and it literally gives you that alternate view. And this notion of looking at things through a different perspective, we often think about that as a switch in our cognitive frame, in our thinking. But also, we now know there's this parallel signal that's sent to the body in which, in order to access these alternate rule sets, new ways of looking at things, there's a calming signal literally sent to the body as well. And I find this conversation fascinating because normally we just think about anxiety and exploration and rule setting and rule responses or responses to rules, et cetera, as a kind of the body sends signals and the brain does all this, what neuroscientists have always talked about as top-down processing. Right, just sort of suppress the hypothalamus, control the limbic system.
Right.
And that's true to some extent, but there's also, it's clear there are signals being sent to the body in parallel. And rather than look at the signals...
It's more like conducting than suppressing.
Exactly.
Like conducting, like an orchestrator conducts.
Exactly. And there's a very interesting phenomenon that takes place in people that have chronic anxiety or for people who essentially stop accessing alternate rules and responses to these signals. And this is, I think, what is showing up in chronic anxiety, certainly in certain forms of depression, and when people enter states of rage and dysregulation, is that normally we know based on neuroimaging that the prefrontal cortex is essentially leading the response of this anterior cingulate cortex and the insula. So information is coming up from the body into the insula, and then being fed to the prefrontal cortex. But then the prefrontal cortex is actually in a position to lead responses, and it essentially is acting like the coach of a team. And the team is all these structures like the ACC and the anterior cingulate cortex and the insula, the heart rate, and so forth. What happens in individuals who have chronic anxiety or damage to the prefrontal cortex or dysregulation of these circuitries is that order actually reverses. The insula and ACC start leading and directing the response of the prefrontal cortex. And I think, we see this I'm sure you've seen this clinically in individuals. And while this isn't necessarily a discussion about society at large, I mean, we see this in dysregulated arguments and dysregulated combat where people is essentially losing themselves and they default to what appears to be very primitive rule set. And it may or may not be the appropriate one. Yep. But you and I, of course, have the good fortune of knowing a number of people who've worked in special operations and things like that. And you talk to any of those individuals, and they know from experience and from training that their ability to access multiple rule sets and options in the moments of extreme autonomic arousal is actually where their power lies, right? It's or a combat fighter, or let's just take, or in debate, right? Something that you're far more versed in than I am, right? Although I guess every academic has to deal with a bit of that coming up, thesis defense, et cetera. In a really good debate, you can't allow the autonomic response to overtake you, or you lose access to an enormous database that resides in one's hippocampus, and you essentially, one then defaults to the bodily state, right? And this is what we see when we see people become dysregulated in rage, et cetera. So if we were to zoom out and then ask, where is the line between exploration and anxiety? I think that we can check off a few boxes for sure. First of all, that autonomic arousal, this tendency to be more alert or more in action than in non-action, is a very healthy response. I mean, the moment adrenaline is released from the adrenals, and as you know, there's a parallel signal in the brain. You get adrenaline released from the adrenals if you get in a cold shower or somebody says something triggering or you are afraid of heights or something. But the brain has its own kind of adrenaline system, which is this structure in the back of the brain called locus ceruleus. And it basically it essentially sprinklers the entire brain with noradrenaline and adrenaline. It's a very interesting system. It lacks specificity. It basically wakes up the whole brain. If I were to put a little, if I were to label the connections of the locus ceruleus, it's basically connected to everything. It just kind of sprinkles a caffeine-like substance on the entire brain, wakes you up. The adrenals in the body wake up the body. So two parallel systems wake us up.
Is that associated with the orienting reflex?
Yes.
If you orient, does the locus coeruleus wake up the brain?
Absolutely. Yes. So it's a key component of the so-called reticular activating system.
Reticular activating system.
Yeah. Yep. And incidentally, I should mention this because I was going to come to this later, but I think it's relevant now. If somebody has a lesion in their dorsolateral prefrontal cortex, or if you transiently inactivate it with a technology, a non-invasive technology like transcranial magnetic stimulation, they can now just put a magnet on outside the skull and quiet that area of the brain transiently. In animals or humans, what you find is that person or human becomes incredibly accurate at any motor task. So for instance, if I were to give you a shooter game where you're supposed to shoot targets, and you're shooting targets, you'll have some hits and some misses, like anybody. If I inactivate your dorsolateral prefrontal cortex, your accuracy goes through the roof. It's near 100%. But the one thing you can't do is decide whether or not you're shooting an enemy or a friend. So you can no longer establish rules. You just become very good at execution of the motor behavior. Similarly, in an animal or person without a dorsolateral prefrontal cortex,
you see a trade-off there, right, between specificity and flexibility.
That's right. And so we see this theme over and over again, where as a purely, sensory motor response machine, the prefrontal cortex isn't even necessary. In fact, if you get rid of it entirely, people become like machines. If I click over here, somebody has no prefrontal cortex, basically everything becomes a stimulus. A puppy, everything's a stimulus. I used to have a bulldog. When he was a puppy, you had to worry about leaving cords out, and everything went into his mouth. By the time he was, a year old, in part because he was a bulldog, you just kind of lay there. Like you could put a toy in front of him and he wasn't into playing and just leave it alone. A baby, everything's a stimulus. Many adults become infant-like in their responses, right? When anxiety is high. In fact, I have a friend who's a psychologist. Tell me if you agree with this statement or not, that anxiety makes children of us all. I don't know if that's true or not, but certainly has been my experience that when feeling anxious, I don't struggle with chronic anxiety, but I certainly have felt anxiety.
Well, it simplifies us. I mean, all these underlying emotions and motivational states, these primordial instincts, are simplification mechanisms. And so if we're unable to compute a complex and sophisticated pathway forward that takes multiple variables into account simultaneously, we can't just do nothing. We're going to default to a more primordial and direct state. And then you might say the whole panoply of emotions and motivations lies there at the weight for us to grip our behavior if we're paralyzed by inability to choose between multiple options. And so we do, to the degree that we're simplified by an emotion, then we're reduced to something more approximating an infantile state. If you watch 2-year-olds, and 2-year-olds are particularly interesting in this regard, they basically just cycle through innate motivational states. It makes them really interesting to be around because when they're interested in something, they're 100% interested in it. And then when they're angry, they're 100% angry. And if they're anxious, they're 100% anxious. And tired, they just instantly fall into a coma. And they just cycle through these with no overarching centralized integration. And it's partly because they likely don't really manifest any integrating prefrontal cortical capacity until they hit about 3, where they can start to engage in joint play states with other children, right? And then they can exercise, then they can modulate their underlying emotions in accordance with an abstract representation or goal, sometimes that's jointly shared. That's part of developing sophistication. It's also why the idea that identity is subjectively defined is absolutely preposterous. It's like, it's subjectively defined for 2-year-olds, but it's not subjectively defined for anyone who's sophisticated enough to negotiate with someone else. And so tell me what you think about this. My understanding of the prefrontal cortex is that over the course of evolutionary time, it grew out of the frontal cortex and that out of the motor cortex more specifically. And so the best way to think about what the prefrontal cortex does in some sense is that it generates potential abstract patterns of action. It generates them in abstraction so that they can be assessed before they're implemented. And so it's like it's generating potential future selves.
That's exactly right.
That's okay.
That's exactly right.
Okay,
and I'm glad you stated it, not I, because you stated it far more clearly and succinctly than I've heard it stated before. It's as if it's running plays. I'm using a sports analogy. It's running plays and thinking about potential outcomes. I'm not a chess player, although Lex Friedman's podcast and Lex Friedman are convincing me that perhaps I should learn because there's a lot of discussion about chess nowadays. And there's a lot of thinking, as I understand, about potential outcomes. How many moves can you anticipate if this, then that? It's sort of if this, then that type of thinking. And if you think about its connectivity, it's in a beautiful position based on its access to priors through the hippocampus, so memory. It can take into account current state, bodily state. It can access information, for instance, about do I have the energy? Do I have the resources to undergo a particular pattern of response. And that's through the insula and the ACC. And then the dorsolateral prefrontal cortex, in this way of also being able to control the body, of being able to calm the body, this is a very unique pathway, because typically we think of the heart rate as going up if we're excited or scared, and heart rate going down if we're calm. But really the default of the neural inputs to the heart and to the breathing systems, et cetera, are to be very activated. And then the brain provides a suppressive or kind of a braking on that entire system. The vagus nerve.
Right, so it's a default on system.
It's a default on system. And the vagus nerve, which of course is a massive nerve pathway. Again, it makes it sound like one little nerve, but it's this huge superhighway of connections between brain and body, is classified in medical school as a parasympathetic pathway, meaning of the calming system, kind of generically speaking. And indeed it is. And so the prefrontal cortex, we can think of as, remember in the seesaw analogy, the hinge. The prefrontal cortex is more or less like the screwdriver that tightens that hinge, essentially make sure that the seesaw stays at a level, at a tilt that's appropriate for whatever it is that you happen to be doing.
Okay, now I presume it does that. So imagine, so to continue the evolutionary analog, so an animal that doesn't have a lot of behavioral flexibility, generally its reproduction strategy is multiple copies of itself, maybe hundreds, maybe thousands. And the reason for that is all the variability in the animal's behavior is genetically coded. And so for it to adapt to the transforming horizon of the future, it has to produce multiple variants of itself, most of which die. With mosquitoes, for example, they produce thousands of eggs. And if they all lived, we'd be knee-deep in mosquitoes in like 10 years. But they almost all of them die because they're not matched to the transformation that's coming down the pipeline. But with human beings, what we seem to have done is evolved a mechanism for manufacturing artificial selves in this game-like manner. And so we can put forward optional selves in abstraction and then kill them off when they're not necessary without us dying. And so the famous quote, I think it was Alfred North Whitehead, was that the purpose of thought was to let our thoughts die instead of us.
I love that.
And it really makes us unique. Yeah, it's great. It's absolutely great. And so, and then it seems to me too, you tell me what you think about this, is that the abstracted artificial selves, avatars in some sense, that the prefrontal cortex generates, or that it allows these underlying motivational and emotional systems to generate, because they can generate simple avatars by themselves. I think when we describe those, we're telling stories. When we describe one of these alternative modes of action, that's precisely it's the verbal description of that is a story.
That's right. And you make a very important point, which is that the prefrontal cortex is a rule-changing, alternate self-accessing machine that can also calm the body. And here I'm making up a just so story because, as I always say, I wasn't consulted at the design phase. And so I don't know why it's set up this way. I just know that it is set up this way. One reason to suppress the somatic response, the bodily response, is that tends to be a unitary interpretation, meaning at this moment I feel alert but calm, so I feel good. But I'm guessing there's a lot of signals coming from the body, and in fact there are to my brain, but I tend to just say, I feel pretty good. In fact, I'm very delighted to be here, so I feel good. Or if I'm very tired, I feel tired. Those tend to be very kind of binned responses, and they're fairly generic. Whereas your description of what the prefrontal cortex does, which is an accurate one, I should say, of imagining different selves and different outcomes, almost requires that we suppress how we feel in our body in the moment. I guess we can look to some of our podcasting colleagues like the Jocko Willinks or the David Goggins, who are either forcing themselves or are somehow up at 4:30 in the morning and pushing through that, what I call limbic friction. The limbic system is saying, I'm tired or I'm anxious, and going against that. So there's literally there's a required suppression of the bodily response in order to imagine how we would feel when we complete this, or how terrible we would feel.
How much of that, so let's parse that into two parts, because you could imagine there's an inhibitory component where you're directly in competition with an underlying urge. So the top-down story is, so for example, if you're responding to something in an irritable way that's being directed to you on Twitter, there's going to be a limbic rage response that's associated with that, which you can then suppress. But then the question there that's quite complex, I would say, is something like, to what degree do you think you're directly suppressing that with the prefrontal cortex? And to what degree do you think you're spinning up an alternative self that, if embodied, wouldn't require that physiological response? And so you're switching to a new identity in which that limbic response is no longer germane.
Yeah.
And so the reason that it disappears is not because you directly suppress it in an inhibitory manner, but because you replace what's necessary physiologically given your new understanding of the territory that you inhabit. I think it's some of both, but I've never been able to really wrestle that through.
Yeah, so I think what you're getting to is, what we know is that the prefrontal cortex and its associated networks contain a near infinite, if not infinite, set of possibilities, right? I mean, of course, it's bottlenecked by experience, and it's bottlenecked by one's imagination. But the number of different possible selves that one could imagine is near infinite if one were to spend time on it. Whereas the number of different bodily states that one can have are actually very finite. And if you think about the autonomic nervous system, and in my laboratory, we've studied this typically in the context of fear and confrontation, that the simplest way to put this in a kind of pop neuroscience way would be to say, we can either be back on our heels, meaning retreating, or we can be flat-footed, sort of calm in our stance, or we can be forward center of mass. We can be in sort of pursuit and or competition. There really aren't other motor responses for an animal, including humans, right? You can either stay put,
right,
back up, or go forward. And this is...
Yeah, well, it's useful for people to know that that's the basic platform upon which emotions are erected too, is that emotions are like signals of those action tendencies, and they are very simple. It's back up, get away, stop, or move forward. And so generally we associate positive emotion with forward movement, and that would be positive emotion that's dopaminergically mediated fundamentally.
Right.
And then the halting would be, well, it can be calmness because there's nothing to do, but it can also be the paralysis that fear induces. And then panic and retreat are they're sort of on the border between anxiety and pain, I suppose. Pain responses.
Yeah, exactly right.
It's complicated yeah.
Yeah, so these three major categories, I think, encompass most, if not all, of the possible responses, as you said, and probably form the base set for all emotions. I mean, my laboratory studied this mainly in the context of fear and confrontation. And one of the reasons we started to explore this was the following. We've all heard of fight or flight, or rest and digest, right? Those correspond to the alertness system and the calmness system of the autonomic nervous system in their kind of extreme forms. But what we observed in animals, and then now in human studies, we published about a year ago, is that when people are confronted with an anxiety-provoking scenario, in our case, we do this with virtual reality because we need to do it in the laboratory, we find their pain point, essentially. And by pain point, I don't mean extreme fear. I mean the thing that can raise their autonomic arousal, that has them in a mode of considering different options and trying to figure out what is strategic and what they're capable of in that moment. Could be heights, could be confrontation with a predator, animal. It varies by person, but everyone has their pain point. Even Navy SEALs that we've brought to the laboratory, or other people from the special operations community, each and everyone has their pain point. What they do in response to that pain point is really what's interesting. And what we found was that the pause or freeze response certainly was associated with autonomic arousal, with stress and anxiety. We measure this in the brain and body. But it was the lowest anxiety response. People always think of panic, just being paralyzed in panic. That's actually the lowest anxiety response. Retreat was the next level up in terms of levels of heart rate change and levels of change within the insula of all places. We actually recorded from human insula through a partnership with neurosurgeons. And then we found that there were a subset of individuals and animals in the parallel animal work that would confront a fear, not necessarily reflexively, but after some consideration, they would lean into the challenge, essentially confront the thing that was making them feel anxious. And it turned out that response, surprisingly, was associated with the highest levels of autonomic arousal. And this
right. So, but that would be heart rate activation, particularly
heart rate activation and a change in what it's called the so-called gamma wave activity in the insula. We had electrodes in the insula, and what we found was that people who were willing to lean into that challenge
Yeah.
The insula took on essentially a change in its activity patterns, this gamma pattern. The heart rate increased, breathing increased, sweating increased. So these are all the marks of an anxiety attack. But here, if you were to just look at the behavior of the person or the animal, what you'd find is that they were marching forward toward their fear. This is and so then...
That's voluntary exploration.
Right.
So now you did an animal study with mice where you showed, if I remember correctly, that the mice that were showing tail flicking, which was a prodroma to that exploratory activity, showed a particular form of brain activity that if you replicated with stimulation was more potently reinforcing than sexual stimulation.
Right. So here's where the surprise came, the additional surprise came in. We thought, okay, wow, well, there are animals, these mice will tail flick in response to a threat, which is essentially saying, come on, let's go, let's fight, whereas other animals would retreat. And that tail flicking paralleled with in the human studies with people being confronted with it. For somebody who's scared of heights, to go through a virtual reality scenario of being up on a high beam between buildings might not sound like a big deal to the average video gamer or to you and me, but is an absolutely terrifying experience for those people. But a subset of them will just march out onto that platform, or will even explore jumping off the platform with the understanding that it's virtual and get very scared, but they will do it. And they also show these changes in insula activity and changes in heart rate and breathing. What was interesting to us was the mouse data told us that if you stimulate the brain area that was associated with all of this, it's an area of the midline thalamus. I don't want to get down into details of structures too much, but it was a very mysterious area, not been explored much before. Had this incredible name of nucleus reunions. Why, I don't know. The neuroanatomists name these things peculiar ways, as you know. But if we were to stimulate that brain area in mice, we could convert a terrified, non-confrontational mouse into a mouse that was willing to confront its fears in a healthy and adaptive way. It wasn't being foolishly running into the jaws of a predator. It was being very strategic in its confrontation. The interesting thing was if we introduced no fear stimulus, no heights, no predator, no nothing, and we just tickle this brain area, what we found is that animals and humans love that feeling. In fact, they will work for that feeling more than they will work for other stimulation. And
so I've got a bunch of questions about that. So the first is, how do you think that's related to hypothalamic dopaminergic release in exploratory states and the psychomotor stimulative effects of drugs like cocaine and amphetamine? And then second, if you put someone in a chronic state of activating that brain area, say you did that by teaching them to approach their fears rather than to run from them, would that produce epigenetic changes that would transform them physiologically?
Okay, so both very important questions. First of all, the dopamine system is absolutely critical here. In the animal studies, we identified, because we could place tracers in the brain and measure connections, that indeed this brain area in the midline thalamus connects directly to the major hubs of dopamine release in the brain. They have names like nucleus accumbens, et cetera, ventral tegmental area.
Right.
So that was great because it confirmed for us that...
So it is tapping the primary approach-related positive reward system.
That's right.
But it's a very major nucleus that allows that to happen, particularly in the face of voluntary approach to feared stimuli.
That's exactly right. And one thing about the dopamine system that's so important and also explains a lot of pathology, but also a lot of human evolution, is that we have basically one major reward system, which is the dopaminergic system. I sometimes like the analogy that, nowadays you hear about cryptocurrency or the dollar versus the euro versus the this versus the that. There's only one currency in all of reality, actually, and it's dopamine. Whether or not it's the dollar-backed dopamine or it's euro-backed dopamine or Bitcoin-backed dopamine, in the end, whether or not someone has $1 billion or $2 is really that currency resides as something that's transacted in the real world, but their notion of power and potential is dopaminergic. And so too, the potential for mates, the potential for food, how much food you have, how much meat you have stored in the freezer tells you a lot about your security and well-being for you and your family, right? And that is translated into a dopaminergic internal representation of how safe and secure you are, et cetera. So this system of fear versus confrontation taps directly into the dopaminergic system. And there's a beautiful set of studies that were done in the 1960s, published in the journal Science, as one of the top journals to publish in. Again, this is not work that I did, but where they gave human beings, the option to stimulate a number of different brain areas, just sitting in the clinic. And some brain areas would evoke feelings of drunkenness, others would evoke feelings of anger, others of sadness, others of sexual arousal. And the area that these subjects all preferred to stimulate the most, in fact, they would just sit there and lever press pretty much all day long, was this midline thalamus area. And the subjective feeling that they reported, I find this interesting and would love your thoughts on this, is one of mild frustration, anticipation of something, although they didn't know what.
Yeah, anticipation.
And it's this idea, I think, that it's tapping into the dopamine system. And the dopamine system...
The dopamine system says something good is going to happen.
That's right. The key...
It says something good is going to happen. Something good is going to happen. And it's an appetitive state in some sense because it doesn't signify the acquisition of... It's not satiating. Right. It's appetitive.
That's right.
And so it drives you forward. And you might think that being driven forward would be unpleasant, but if you're, in some sense, if you're activating the systems that drive you forward voluntarily, then that's the most positive form of positive reinforcement you can have. I think I read animal researchers who said that when they watched animals who were bar pressing to receive stimulation in those brain areas, the animals would look forward as if something was about to appear that they wanted to have appear.
Incredible.
So that was part of that apprehension. Part of it's a hope system in some sense. Right? It's the elicitation of hope.
That's right. You know, it's dopamine, and here I'm robbing words from others, like my colleague Anna Lemke, who, you know, it's not about having, it's about wanting. It's not about pleasure as much as it is about craving and motivation and drive. And something critical about
And Panksepp called it seeking.
Yeah, brilliant. I never met Panksepp. Did you? You met Yuck?
I met him online. We were in a neurological chat room, so to speak, for a neuropsychological chat room for about 5 years, and I had a chance to interact with him a fair bit in that. So that was really good.
I'm envious. He's done beautiful work, and thank you for calling people's attention to his work. I know you've done that many times, and such key work. The dopamine system is in touch with the autonomic system, sure, because it has to register success versus failure of some pursuit. The prefrontal cortex is actually part of the dopamine reward system. People often overlook this, and then we just think about nucleus accumbens and ventral tegmental area. But the prefrontal cortex, because, as you pointed out before, it is generating possible outcomes, different rules, different selves are being projected into the future. You can think that the 2 marshmallow task, the classic, give kids the option to either have a marshmallow now or wait and have 2 marshmallows, and the cute little videos of the kids, in the room with the marshmallows, sniffing it, talking to it. Occasionally a kid will just stuff it in his mouth. Another child will turn away, delightful, right? And all sorts of ideas have come about how they do in life versus if they can wait or not wait. In any case, that's dopaminergic anticipation. The key thing with dopamine, I think, that encapsulates the most of it is this notion of reward prediction error, which is very simple. If you are excited and anticipating something, you are generating some internal sense of the probability of it happening. We're going to the ice cream store, kids. Let's go. We're going to have ice cream. We have ice cream. It's closed. The disappointment that they experience actually brings them far lower than they would feel, much more sad than they would feel than had you not told them you were going to get ice cream, which speaks exactly to what you were saying, that it's an anticipation signal. So dopamine's going up, we're going to get ice cream, and then no. So it drops below baseline. They would have been better off being not told they were going to the ice cream store. Just drive right by it.
The danger of hope.
The danger of hope. If you anticipate that it's going to be open, and again, this could translate to any scenario, and it's open, there's a dopaminergic signal upon receiving the reward, but it then drops a little bit. This is the basis of addiction, actually. Drops a little bit below baseline transiently. So we always think of the ice cream is the reward. Well, actually, the reward was right before you had that first lick of ice cream because you know you're going to get it. This is also true of sexual behavior. It's true of people who sell a company or they're anticipating something exciting, or of a wedding. It also sort of partially explains this notion of postpartum depression, where people are so excited about something, the delivery of a child or something on the arrival, and then for some reason they feel let down. It's because the anticipation was that great. So many scenarios.
There might be an exhaustion component there too.
Right.
Well, it's also the case, if I remember correctly, that dopamine kick, so imagine what it does is backtrack the neural systems that were activated as the reward was approached. So then it feeds back reinforcement, not reward, but mediates cellular growth and maybe myelinization. It's increasing the efficiency of the neural connections of the systems that were activated just prior to receiving that reward in the order they were prioritized,
That's right.
in the order they were manifested. So the closer the behavior is to the receipt of the reward, the more it's reinforced and more likely to be manifested in the future. And then there's a decay function going back in time. So, and that's partly how an addictive subpersonality can grow too, right? Because you can imagine that there's a certain state of mind that you're in. Maybe it's a state of something approximating nihilistic hopelessness that grips you every time you're motivated to seek out your favorite drug. And that's fairly far back in the activation chain, but it's there every time you take a hit. So what happens is the dopaminergic reinforcement produced by the drug reinforces that nihilistic hopelessness that drives the drug-seeking behavior.
That's right.
And that's how, in part, you develop a monkey on your back.